Okay, shall we start?
Yes, sir.
আমার কথা শোনা যাচ্ছে?
Yes, sir.
Yes, sir.
Okay. So in the last class, I believe we had obtained the variational statement or the variational form of the Euler-Bernoulli beam equation. So please correct me if I am wrong. This is what the expression looks like: EI W double prime V double prime dx equals integration 0 to L Q V dx plus P times V at L plus, again, I'm still talking about that example with the cantilever, which has all the loads that it can have, which is basically this distributed load. Again, please remember, positive y is positive, negative y is negative, and we'll be showing everything in the positive direction. So that is the distributed force Q. The direction along the axis is x. The concentrated force at the free end is P, and that moment at the free end is m0. And in the last class, we also discussed why the position of the couple moment also matters if we are talking about deformable bodies. m0 times v prime at L. Okay, so this is the weak form. So this comes with the boundary conditions as well. Okay, except for, I mean, it comes with the essential boundary conditions. The natural boundary conditions. These two are the natural boundary conditions, and this is true for all v. When v is 0 in gamma w and v prime equals 0 in gamma w prime, both of which exist at x equals 0. Okay, so having said that, let's proceed for the Fe formulation of the beam element. So now imagine I'm trying to model this beam as a single beam element. Okay, and at each, sorry, okay, so so again we have our natural coordinate which goes from -1 to 1 across the length. A physical coordinate, it goes from x1 to x2 Okay, and there are other quantities that I'll show on the element itself. So the degrees of freedom. So this is the vertical deflection W1, and on the other end it is W2. Actually, by the way, I should be going with the node numbers. So this is node number 1, this is node number 2, this is the element 1. Okay, and there are two more rotational degrees of freedom. Okay, and this one is theta 1 and this one is theta 2. Okay, and since the beam deflects, so we have done all the assumptions associated with Euler-Bernoulli beam theory, including W prime is much smaller than 1, which basically means that the theta 1 is tan inverse of W prime evaluated at x1 originally, which is approximately W prime at x equal 1. Okay, because you see this is much smaller than 1, the absolute value of it rather. Okay, and this is also the same reason why we say that the radius of curvature, which is 1 plus W prime squared to the power 1.5 divided by W double prime. Okay, we said that this is also 1 by W double prime, hence everything associated with the Euler-Bernoulli beam theory. So this is how we represent this. Okay, acha, and similarly goes V. So now here we would deviate from whatever we have used so far. So beam element is not an isoparametric element, which means the coordinate and the degrees of freedom are not mapped with the same set of shape functions. Okay, the coordinate is simply this. So x is simply 1 minus I by 2 x1, very familiar from the bar formulation, um, 1 plus I by 2 times x2, which also leads to j defined as dx. This is the definition sign. Dx dxi is basically the element length divided by 2. So these are the shape functions used for mapping the physical coordinate. But when it comes to mapping the degree of freedom, okay, this is how we represent it using a cubic function. Okay, so beam theory uses Hermite polynomial. I'm not writing it because I'm not confident with the spelling itself. Okay, but you should look for what type of functions, shape functions do beam elements use. So they are Hermite polynomials which are cubic in nature. So basically I should be able to write it as C0 plus C1 xi plus C2 xi squared plus C3 xi cube. Okay. Mm, now I can obtain these values of the coefficient C0 through C3, okay, by doing some substitutions. What sort of substitution? The substitutions are these: W at xi 1, or you see W at xi equals minus 1 is W1, and W at xi equals 2 is sorry, not 2, it is 1 plus 1 is W2. Okay. Now, this is very straightforward. What is not is this quantity W prime at xi equals -1. Okay. Now, please remember what this quantity is. This is dw dx evaluated at xi equals -1, which is dw dxi times j inverse evaluated at xi equals -1, which basically says 2 by le dw dxi at xi equals -1. Okay, and that quantity should be theta 1. Similarly, theta 2 is 2 by le dw dxi evaluated at xi equals 1. Now, if I club this four conditions, or if I make this four substitutions, I would get a set of linear equations. Okay, and that would look somewhat like this. Oh, I shouldn't be deleting those. I would get a set of equations which would look somewhat like this. C0, C1, C2, C3. If I take a derivative of W with respect to xi, this is what it looks like. C1 plus twice C2 xi plus 3C3 xi squared. Okay. And here we have the right hand side, which is W1 2 by, okay, no, not 2 by, but Le by 2 theta 1, W2 Le by 2 theta 2 is this quantity. Now, you see, if I substitute xi equals 1, so the first row should be the values corresponding to that. I mean, the values of xi to the power 0, xi to the power 1, 2, 3 corresponding to -1, which basically is 1 minus 1. Sorry? 1 minus 1, 1 minus 1. Similarly, when we come to the third row, this is how it is going to look like: 1, 1, 1, 1. And when we compare the, when we write the second row, please remember there is no coefficient for C0. Okay, so this thing is 0. This one is -2. No, sorry. This one is 1. This one is -2. And this one is 3. And when it comes to the fourth row, it is 1, 2, and 3. Okay. Now, what we should be doing is we should be solving for C0, C1, C2, C3 in terms of W1, theta 1, W2, theta 2. Okay. So can you do that solution? Can you give me the expressions for Ci's with respect to Wi's and theta i's?
স্যার এই জিনিসটা একটু বুঝতে পারলাম না স্যার, এই ম্যাট্রিক্সটা যেরকম করলেন, তো এটা কি লোড ভেক্টরটা? না না, লোড
এখানে কোনো লোড ভেক্টর গল্প নেই, এখানে কোনো স্টিফনেস ম্যাট্রিক্সের গল্প নেই। ওকে, উই আর still away from the load vector or the stiffness matrix or the degrees of freedom. What we are doing is we are just getting an alternative representation. You see, I can represent a cubic equation in general like this, but if I were to satisfy these conditions, okay, so in terms of the degrees of freedom, so these are general coefficients and these are the degrees of freedom. So how do I represent W in terms of degrees of freedom? Then whatever
Okay.
polynomial
Okay.
would be the coefficient of the degree of freedom, we would call them as shape
Hmm.
functions. So what you are trying to do here is trying to get the shape functions. Okay,
আচ্ছা
so I don't need the representation in terms of C0 to C3. I need the representation in terms of W1 to theta 2. Okay, so I need to represent C0, C1, C2, C3 with W1 theta 1, W2 and theta 2. The substitution happens through satisfying these conditions, these boundary conditions. এই অবধি বোঝা গেল?
ইয়েস স্যার
আচ্ছা, এটা করা যাবে কি? একটু মাথা খাটিয়ে করলে কিন্তু খুব সহজে হয়ে যাবে। যেমন ফার্স্ট ইকুয়েশনটা আর থার্ড ইকুয়েশনটা, if you add them up, two of the coefficient will vanish, and if you subtract them, two other coefficients will vanish. Okay, if you look at the equation number 2 and equation number 3, if you add them, only two coefficients will survive, but if you subtract them, only one coefficient will survive. এইগুলো একটু যদি মাথা খাটাও তাহলে দেখবে খুব ইজিলি এই সলিউশন গুলো পাওয়া যাচ্ছে। ট্রাই করো নিজেরা। I mean, you can get C2 real easy. C2টা কি পাওয়া যাচ্ছে?
So minus LE theta 1 by 8. Oh, minus
C2
theta 1.
you're supposed to subtract this this from this. যদি C2 পাওয়া যায়, then C0 is W1 plus W2 by 2 by adding the first and the third equation. minus C2, which is LE by 8, theta 2 minus theta 1.
Sir, C theta LE by 2 theta 2 minus W1.
No. C3, I have got a different expression, but so I'll have to check. Let's say if I add the second and the fourth equation, I'll have C1 plus 3C3 equals LE by 4 theta 2 plus theta 1. Okay. And if I subtract the first equation from the third equation, I'll have C1 plus C2 equals W2 minus W1 by 2. Okay. Now from these two, if I subtract this new equation 2 from new equation 1, then I'll have twice C3 equals LE by 4 theta 2 minus theta 1 minus W2 minus W1 by 2. Then I will divide with 2 and end up having this expression. And that's what I've got also. And if you subtract this from this expression over here, then you have C1 equals W2 minus W1 by 4 times this minus, actually this one is plus actually, right? Minus LE by 8 theta 2 plus theta 1. We can represent these 4 terms, okay, in this row of degrees of freedom as U1, U2, U3, and U4, which means U1 is W1, U3 is W2, U2 is theta 1 but with a coefficient LE by 2, and U4 is LE by 2 times theta 2. Okay, so substitute for these values of C1, C2, C3, C4, sorry, C0, C1, C2, C3 in the expression of W. Okay, and then find out what are the coefficients, of Uy. Okay, multiplying theta 1 and theta 2 with LE by 2 is simply a scaling operation. Okay, because in one case you are taking derivative with respect to x, in another you are taking derivative with respect to xi. So that's what has happened over here. If you take derivative of something with respect to xi, the dimension doesn't change, but if you take derivative with respect to x, dimension reduces So to take care of that dimension, LE by 2 is multiplied. So find out the polynomial coefficients of ui's. In the end, you should be in a position to write it as summation ni uy, where ni's are the polynomials in xi, or something like in u hat. শেপ ফাংশনগুলো পাওয়া গেছে?
স্যার করছি স্যার।
আচ্ছা, করো।
স্যার C1 টা হবে LE by 8 into 5 theta 2 minus theta 1. হ্যালো,
কিসের কথা বলছো? C1?
স্যার
C1 এর এক্সপ্রেশন এই তো এখানে লেখা আছে, দেখো স্ক্রিনে লেখা রয়েছে। I said you substitute for C0 through C3 in the expression of W, and then write in terms of ui's and see what are the polynomial coefficients.
স্যার ওই U1 ইকুয়ালস টু W1 আর U3 ইকুয়ালস টু W2 এই পার্টটা কি হলো ওটা বুঝলাম না।
স্যার আপনার অডিও মিউট করা আছে।
হ্যালো
হ্যালো স্যার আপনার অডিও মিউট করা আছে।
সরি। আচ্ছা, এবার শোনা যাচ্ছে?
হ্যাঁ
হ্যাঁ
স্যার।
স্যার।
আচ্ছা, তো মানে so this is how we have defined the 4 degrees of freedom. U1 is W1, so I mean this is just another way of calling them. Okay, so in the end I want W to be represented in terms of NIs and UIs. So can you tell me what are the NIs?
স্যার N1 টা 1।
N1 টা মোটেই 1 না। W1 would be present in C0,
না N2 টা
then
আসছে 2W2 minus W1 by LE theta 1।
না তুমি দেখো গুলিয়ে ফেলছো, এখানে অনেক কিছু রয়েছে। You see these CIs are the coefficients, ঠিক আছে, and we just figured out satisfying some boundary conditions that they could be represented in terms of Wi's and theta's that we have already done. So there is C0, there is C2, there is C3 and C1. Okay, but then if you substitute C0 through C3 in the expression of W where it is a cubic function, okay, of xi with Ci's as the coefficients, so from there you will get a representation involving the polynomials of xi and Wi's and theta's.
ওকে ওকে হ্যাঁ।
হ্যালো স্যার।
হ্যাঁ বলো
স্যার বলছি N1 টা কি
বলো।
মানে N1 টা 1/2 মাইনাস 3/4 জাই প্লাস 1/4 জাই কিউব এরকম কিছু এসছে মানে আসবে 1/2 মাইনাস 3/4 জাই প্লাস 1/4 জাই কিউব N1 টা।
আমার এসছে n1 equals half minus 3/4 xi plus 1/4 xi cube.
হ্যাঁ স্যার ওটাই এসছে ওটাই এসছে।
So the last class we discussed about Galerkin's method, which is one of the weighted reservoir methods. n1 টা এসছে half minus 3/4 xi plus 1/4 xi cube. ওকে, এটা ঠিক আছে?
হ্যাঁ স্যার।
হ্যাঁ স্যার এটাই এসছে।
আচ্ছা,
স্যার n2 টা হচ্ছে 1/4 জাই স্কোয়ার মাইনাস 1/4 জাই প্লাস 1/4 জাই কিউব।
আচ্ছা দেখো
n2
এগুলো এসছে কিনা। ওকে, এই চারটে এক্সপ্রেশন দেখো, এইগুলো এসছে কি? দেখা যাচ্ছে?
হ্যাঁ স্যার এসছে।
হ্যাঁ স্যার ঠিক আছে।
ঠিক আছে তো? আচ্ছা, তাহলে এবার আমার কয়েকটা কথা বলার আছে রিগার্ডিং দিস এক্সপ্রেশনস। লেটস লুক at n1, okay, and then take derivative of n1 with respect to xi. Acha, so if I do dn1 xi, I'll get this expression 3/4 plus 3/4 xi squared. Okay, এটা এলো তো?
হ্যাঁ স্যার।
আচ্ছা, do the same thing for n2, n3, n4 এর জন্য করতে হবে না। You will understand what I'm trying to say, okay, once we show that for n1 and n2. So if I do that for n2, I'm supposed to get this expression. Okay. Acha. Now evaluate n1 at at the two ends. So at the two nodes. So there is node number 1 and node number 2. Xi values are -1 and 1. Okay. So now at -1 and 1 of xi,
স্যার বলছি ওটা 3 হবে না, 3/, মানে 3 xi স্কয়ার হবে না ওটা, dn2 এর
কোনটা?
যে এক্সপ্রেশনটা আছে স্যার, dn2 dxi যে এক্সপ্রেশনটা আছে ওটা 3 xi স্কয়ার হবে, মানে
3 xi squared. Yes, 3 xi squared. Correct. Acha. Now evaluate n1 at -1. What is the value?
One.
1. What is the value of n1 at 1? n1 এর ভ্যালু 1 এ কত হবে?
0.
0. What is the value of dn1 dxi at plus or minus 1? এই কোয়ান্টিটির ভ্যালু at xi plus or minus 1 কত হবে?
0.
0. Which means this is how the shape function looks like. Let's say this value is 1. So this is how the shape function looks like. The slope here is 0. And the slope at the other end is 0. The value at the other end is 0. And the value at this end, left end, is 1. That means with n1, n1 is such that if you have 4 degrees of freedom, let's say w1, theta1, w2, theta2, okay, it is such that if you keep this quantity 0, this quantity 0, and this quantity 0, and this quantity equal 1, okay, then the shape of the beam should be the shape function.
স্যার এটা আরেকবার বলবেন?
So that is how the shape of the cubic curve should be, right? So that's what you get out of n1. Now try the same with n2. Evaluate n2 at -1. Evaluate n2 at +1. as you may have already figured out, N3 would look something like this. Okay, but what is the value of N2 at -1 and +1?
জিরো স্যার, দুটো
দু ক্ষেত্রেই 0, তাই তো?
yes sir,
What is the value of dN2 dxi at 1?
one is 0 or -1 is 1?
yes sir, one
So this is 0
zero,
and this one is 1, which means the curve looks like this. So this is your slope at the left end is 1, which means this angle is physically 45 degree. তার মানে N2 is a shape, okay? N2 is the function, okay? If the coefficient of all other shape functions were to be 0, that means W1, W2 and θ2 were to be 0. This is how the beam would deflect. Okay. Now, obviously, in physical situation, the slope of the curve would not be 1, and neither would the angle be 45 degrees. It's because you see, there are a couple of other things multiplied to it. The value of the θ1 matters, okay, and the length also matters. So it is the coefficient to all of this, okay. But this can be the schematic representation of the shape, how the shape would look like if all other degrees of freedom were at 0 and this was non-zero. Okay, ঠিক আছে? তো এই অবধি বোঝা গেল?
স্যার ওই জিরোতে ওইটা এই N1 and N3 এর নিচে ক্রস করবে না?
কোনটা?
এই জিটা ইজ ইকুয়াল টু 0 তে N2 এর ভ্যালুটা হচ্ছে আপনার 1/4, আর ওই N1 আর N3 টা হচ্ছে হাফ, তো ওইটার N1 আর N3 নিচ দিয়ে যাবে N2 টা
N2 টা
at 0
when
at 0
xi is 0, dN2 dxi is, you see, dN2 dxi is negative, but N2 is positive.
তো
So we
ওইটা
are plotting
N1 আর N3 টা যেখানে ক্রস করছে ওই ইন্টারসেকশনটা নিচ দিয়ে যাবে না?
হ্যাঁ, ওটা একটু নিচ দিয়ে যাবে, ওটা আমার আঁকাটা ভুল হয়েছে, মানে it would be below this, but মানে সেটা হয়তো আমার আঁকাতে ভুল হচ্ছে এখানে, কিন্তু মানে ফিজিক্যালি যখন করবে সেটা হয়তো বেশি হবে, মানে ডিফারেন্ট হবে, ঠিক আছে? আমি শুধু মানে দুটো এন্ডের ভ্যালুগুলোতেই কনসেন্ট্রেট করেছিলাম সেই জন্য। আচ্ছা, নাও N4 would actually be a little interesting. It's because this is how it would look like. The value and the slope is 0 at -1, but then the value is 0 at 1 also, but the slope should be positive. Okay, so this is how N4 would look like. ঠিক আছে?
Yes sir.
Okay, so now No, I shouldn't be deleting those, right? So we'll be using these shape functions to get the FE formulation. The reason I showed you these shapes actually, it's because if you follow, let's say, R.D. Cook's finite element book, so they are actually the functions themselves. So we did a lot of exercise to arrive at the form of the shape functions, but this is how they would determine the shape functions. Okay, so so now I can write W to be N1 LE by 2 times N2 N3 LE by 2 times N4 times W1 theta 1 W2 theta 2. Okay, and this point onwards, this should be our U hat. Okay, so I'm supposed to take double derivative of W with respect to X, and that is ddx of W prime, and as we already know, that is J times dW d xi. So from this, again, we can write it is supposed to be, sorry, what did I do? It is not J times, it is J inverse times this. So 1 by J squared d2W d xi 2. Okay, now that essentially turns out to be 1 by J
স্যার
squared.
ডিএক্স ডিজাই হবে না?
হ্যাঁ, dx d xi হবে তো, J is dx d xi, dx d xi. Okay, so when I'm taking derivative, it is supposed to be this W prime is dW dx, right? So it is dW d xi times dx d xi, sorry, d xi dx or J inverse. Same thing would happen again over here. So this ddx, I can write it to be dd xi, then d xi dx, which is again 1 by J. বুঝা গেল?
হ্যাঁ স্যার।
Okay, so next thing is I'm supposed to take double derivative with respect to xi. I suppose that shouldn't be a problem. Achha, by the way, this is LE by 2 d2n2 d xi. Okay, তাহলে এই পার্টটা করে ফেলো. So once you are done with this, this whole thing becomes your B matrix. I mean, whole thing, even with 1 by J squared. So that whole thing becomes your B matrix. Okay, and as you may have already figured out, this integration zero to L EI W double prime V double prime dx. That is what it is supposed to give you the stiffness matrix. But then again, V double prime can be taken as V hat transpose B transpose. So we are going to get V hat transpose B transpose EI. So this is going to be 4 cross 1, 1 cross 1, then B 1 cross 4, a 4 by 4 matrix, times J d xi going from -1 to 1. Then in the end, multiplying with U hat. Okay. So whatever is within this parenthesis, set of parentheses, is our element stiffness matrix. Okay. So derive the expression for element stiffness matrix. বি ম্যাট্রিক্সটা পাওয়া গেল?
স্যার
Yes.
আচ্ছা, তো যদি এলিমেন্ট স্টিফনেস ম্যাট্রিক্সের মধ্যে দেখো So EI is, if we assume again, this is where for the first time we are making this assumption that the Young's modulus and the cross section are uniform across the length. So we can bring them outside of the integration. Okay, so all we got to do is multiply B transpose with B and then do the integration. So element stiffness matrix, as you can see, it is B transpose B. It is obtained by integrating B transpose B. So essentially, it is going to be symmetric. And therefore, it means we'll have to evaluate only the 10 terms from the upper triangle. Okay. I believe one term is 12 and three term is 12. স্টিফনেস ম্যাট্রিক্সের টার্মগুলো পাওয়া যাচ্ছে?
স্যার করছি।
আচ্ছা,
এই পার্টটাতে একটু ইস্যু হচ্ছে বুঝতে। এই বি
আচ্ছা,
ট্রান্সপোজ এইটা এইটা তো যেরকম জিটার টার্মস আসছে,
কিসের টার্মসে?
বি বি বিটা
হ্যাঁ,
বিটা এই যেরকম জিটার টার্মসে আসছে।
হুম।
হ্যাঁ, তো এই ইন্টিগ্রেশনটাতে একটু ইস্যু হচ্ছে করতে। আগের দিনও ওই প্রবলেমটাতে একটু ইস্যু হচ্ছিল কিউবিকটাতেও, কোয়াড্রেটিক বিমটাতেও, যে এই পার্টটা
স্যার
ইন্টিগ্রেশন কি হচ্ছে ওইটা একটু।
মানে জায়ের টার্মসে আসছে কোনো টার্ম, ধরা যাক ইফ ইউ টেক n1, n1 is 1/2 minus 1/4 xi, right? Plus 3/4 xi cube, তাই তো? Is this n1
1/4 যাই কিউ ছিল,
1/4?
হাফ মাইনাস 3/4 যাই প্লাস 1/4 যাই কিউ।
Okay. So if I take
ডাবল ডেরিভেটিভ
n1 d xi, or rather if I take two derivatives, so it is going to be, so first two terms are
3/2
going, so the next term is
3/2 জিটার।
3/2 xi, right? Okay.
এরকম করে পুরো বি ম্যাট্রিক্স হচ্ছে।
হ্যাঁ, এরকম করে পুরো বি ম্যাট্রিক্সটা আসবে। So when you do b transpose b, so there would be total 16 of such terms.
16, হ্যাঁ।
So let's say this is n1, so the first term should be
9/4 zeta
xi
square.
square.
Uh,
Okay, so you'll have to integrate that between -1 and 1. For example, if this is n2, or for that matter, let's start with n3. N3 is half minus or plus, what is n3? N3 is half
half
plus
plus
3
3
by
by
4
4
xi
zeta minus 1/4 zeta cube.
minus 1 by 4 xi cube, right? So if I take double derivative,
না মানে আমি প্রত্যেকটা এলিমেন্ট ম্যাট্রিক্সে ইন্টিগ্রেশন করবো তো?
now this is the 1 1 term, right? So the 1 3 term should be uh, minus 9 by 4 xi squared. 3 3 term, so 1 2 3 4, 1 2 3 4. So the 3 3 term should be again plus 9 by 4 xi squared. Okay, and if I only concentrate on the upper triangle, okay, obviously 3 1 term is same as 1 3 term. Okay, so this is again minus 9 by 4 xi squared, but let's not go there. Let's stick to the upper triangle. Okay, so I can also determine the other terms. For example, if I now determine d2 into d xi2, so that is going to be minus half, and then 1 by 3 by 4 xi, or 3 by 2 xi, right? So this is d2 into d xi2. Okay, now if you look carefully, if I try to do n1, if I multiply these two terms, okay, so the first term would be an odd function of xi. Okay, that I don't need to integrate because the odd function integrated between -1 and 1 is going to be 0. The second term is the only, you see your even function, and that I'm supposed to integrate. But then you see with this one there would be another term which is LE by 2. Okay, so LE by 2 would come inside of the integration. Okay, unless of course you want to use u2 as LE by 2 times theta 2. Okay, that way you can keep LE by 2 out of the out of this integration. Okay, but otherwise this will come inside the matrix. Okay, so the only term that you are supposed to integrate is this product. So again, 9 by 8 LE xi squared. Okay, similarly you can find out how much is d2 n4 d xi2, and for me that turns out to be 1 by 2 plus 1 by 2 plus 3 by 2 of xi. Okay, you see when I'm multiplying, so what I did, I first wrote the derivative, and then when I put it in the matrix, then I omitted the odd function. Okay, but before that I'm supposed to be doing the product, because when I'm doing d2 into d xi2 times d2 into d xi2, or d2 into d xi2 d2 n4 d xi2, even this half can possibly give me an even function. So I need to do the multiplication first and then only put the even functions in the matrix. Okay. So again, for the first row, this turns out to be 9 by 8 LE xi squared. Okay. So I have 1, 2, 3, 4 terms. Okay. And then I can figure out many other terms. For example, the 3, 4 term should be a minus 9 by 8 LE xi squared. Okay. So in this way, I can figure out all the terms.
স্যার হ্যালো
হ্যাঁ বলো।
স্যার EI বাই এল কিউব বাইরে আর ফার্স্ট রো বরাবর এলিমেন্ট গুলো 12 6 LE মাইনাস 12 6 LE সেকেন্ড রো বরাবর এলিমেন্ট গুলো 6 LE LE স্কয়ার মাইনাস 6 LE মাইনাস LE স্কয়ার
So
থার্ড রো বরাবর
12 and 6 LE তারপর
মাইনাস 12
then
মাইনাস
6 LE।
ইয়েস স্যার
এটা কি মাইনাস 6 LE না LE?
শুধু 6 LE স্যার
আচ্ছা তারপর
6 LE সেকেন্ড রো বরাবর ফার্স্ট
সেকেন্ড রো বরাবর প্রথমটা হচ্ছে 6 LE,
ইয়েস স্যার
তারপর
LE স্কয়ার LE স্কয়ার
L squared
LE স্কয়ার
LE squared।
ইয়েস স্যার
Okay,
মাইনাস 6 LE
আচ্ছা
মাইনাস LE স্কয়ার
minus LE squared।
ইয়েস স্যার
Okay, but what I believe is this is going to be 4 LE squared and this is going to be 2 LE squared. Okay, এটা একটু চেক করো। আচ্ছা তারপর এখানে কত, এই টার্মটা কত?
6 LE
minus 6 LE আমার মনে হয় because of this negative sign. You see
ইয়েস স্যার
এখানে একটা নেগেটিভ সাইন আছে, এখানে একটা পজিটিভ সাইন আছে, so it would be different and in the end এখানে আরেকটা 4 LE squared হবে। Okay, and rest are symmetric, which means this one is minus 12, this one is 6 LE, and this is the 2 3 term, so the 3 2 term is also minus 6 LE. Then 4 1 term is already done. 4 2 term is a 2 4 term, that is 2 LE squared. Then 4 3 term is this minus 6 LE. Okay, so this is what the beam element stiffness matrix should be. And one fun thing about this is that unlike bar element, we not very often we use more than one element to model a beam geometry. Typically one element is sufficient. You can already identify the reason being that the shape functions are already cubic. Okay, but unlike whatever rule we imposed on our shape functions, for example the Kronecker delta rule, we couldn't do here. We cannot say sigma ni equals 1. No, this is not true. Okay, actually n1 plus n3 equals 1 because these are both coefficients of your w1 and w2. Similarly, you can say n2 actually dn2 dxi plus dn4 dxi, this equals 1 again because these are coefficients of LE by 2 times theta I. Okay, so it is not very similar to our isoparametric shape functions. Okay, And also, when we are talking about Ni Xi J rule, okay, that is also not true here. Okay, because here you'll have to think in this way. At the first node and in the second node, these are not single locations. These are actually two locations. One is the regular value of the shape function. The other one is the derivative of the shape function with respect to xi. If you think in this way, then actually this second rule applies. Okay. Now, having said that, this is what the element shape function must look like for Euler-Bernoulli beam element. Okay. Please remember, we are considering in this case, we would be getting the LE terms in this expression. Okay. Only if we take U2 and U4 like this, multiplied with LE by 2. Sorry, I made a mistake. No, it's not U2 is, no. This is not how you are supposed to take. You are supposed to take U2 to be theta 2 and U4 to be, U4 to be theta 2 and U2 to be theta 1. And actually N2 is LE by 2 times whatever that polynomial with xi is, that is 1 by 4 times 1 minus xi plus, minus xi cube. Oh, sorry, minus xi squared plus xi cube. So it should have LE by 2. The shape functions we did for bar didn't have the physical length in it, but with beam element, they should be there. Okay. Now comes the next part. So this goes for the left hand side. The stiffness matrix is already done. So you have your element stiffness matrix. Okay, multiplying your degrees of freedom, W1, theta 1, W2, theta 2. Okay, so in the right hand side, there would be 3 force vectors. One due to the distributed load, actually 4 of them should be there. So Q times V dx is there. Okay, the other one being P times V at L. Again, I'm considering the cantilever beam example. Then other one is M0 times V prime at L. Okay, and then the next term would be the ones with the reaction forces and reaction moments. Okay, since we are talking about a cantilever, we know there is going to be one R1 and then one MR1 at the fixed end, the other two are 0. P times VL, you know already how it should look like. It would look like zero, zero, P0 for us. And sorry, this V hat won't be there, right? This V hat won't be there because we had already taken out V hat transpose. So it should be the N matrix evaluated at L, and this is the N prime matrix evaluated at L. So, I mean, derivative of N with respect to X matrix evaluated at L. Okay. So the next term contributing to the force vector. Actually, the term force here is a general term used for forces and moments. Evaluated at L should be 0, 0, 0, M0. Okay. So we only need to take care of this part, the distributed load. And as you may have already figured out, so this is not going to be V. V should be replaced with N transpose V transpose. So this is going to be Q times N transpose. Okay, now this Q can be a general function of X or Xi. Okay, I'm just keeping it as a function of X. And I'm still doing the integration with respect to X, but this dx is essentially d xi times j. And when you integrate with respect to xi, the limits change from 0 to -1 and L to +1. And N transpose is supposed to look like this. So we already know what our N1 is. N1 is something like 1 by 2 minus 3 by 4 xi plus 1 by 4 xi cube. And in 2 we had just discussed 1 by 4, 1 minus, actually L by 2 times 1 by 4, 1 minus xi minus xi squared plus xi cube. Okay, and so on. So we are supposed to substitute n1, n2, n3, n4 over here. Again, you have the choice to either consider theta 1 as a degree of freedom. Here we are doing that, or instead multiply L by 2 with theta 1, so that you don't have to multiply L by 2 with n2. You still have the choice. Okay, but then the same way the element stiffness matrix should be evaluated. Okay, so so since we are not doing that, we are simply using w1 theta 1 w2 theta 2 like this. So this is how we are supposed to take the shape functions, and if you integrate this, you will have the force vector and you can solve. Okay, so এই পার্টটা বোঝা গেল কি, না এই পার্টটা নিয়ে কনফিউশন আছে?
নো স্যার, বোঝা গেছে।
আচ্ছা, বোঝা গেছে তো? এবার আমি দুটো অ্যাসাইনমেন্ট দেব। Assignments. Question 1. If solution for cantilever, okay, single element, use only one element, that is fine. Okay, with following cases. Q equals 0, M0 equals 0, P equal 100 Newton. B, Q equals 0, M0 equals 100 Newton meter, P equals 0. C, Q equals 100 Newton per meter, M0 equals 0, P equals 0, and for all of this, E equals 200 GPa. This is the cross section. Dimensions, as you can identify, are in millimeters. So this is the cross section. So you can figure out the I value, and L is 1 meter. Okay. So for each case, determine W2, theta 2, obviously W1 and theta 1 at 0, and accordingly find out R1 and MR1. Okay. Solve for these four quantities. And not only that, compare the solution that you get from the closed form version of it. That means when you do not use finite element method, but you use your technique from strength of materials. So basically you integrate the expression ei quadruple prime equals q. When you integrate this equation, solve from there. Okay, the reason I gave you this is also very evident. If q is 0, okay, then the actual solution itself is cubic. Okay, and therefore with cubic shape functions we would get exact solution from finite element method, but with a non-zero q we would get an approximate solution. And I need you to appreciate the fact that in some cases you do get exact solution, in some cases you get the approximate solution, and to have a comment on how much of the approximate solution is when you have a distributed load. Is it really off? It is extremely different, or is it somewhat close? Okay, I need you to comment on that. Acha. One more thing, that I have made the problem simpler. In the first case there is only a concentrated force, in the second case there is only a concentrated moment, in the third case there is only a distributed load. But by the very fact that this is a linear problem involving linear elasticity and no nonlinear geometric interpretation, so in this case we can linearly superimpose a solution when we have all the three. When we have all the three different types of loads, we can linearly superimpose them and get the solution. This is our question number 1, and next comes the question number 2. I need you to solve this a problem involving this simply supported beam with so this is, let's say, 1.5 meter and this is 1 meter. Okay, and I'm applying a load of 100 Newton. Okay, the same cross section from the first problem, cross section is the same. Okay, and I need you to solve for the deflection over here. Okay, and slope over here, and slopes at the two ends. Okay, and as you have guessed correctly, taking two elements would do the job very easily. Okay, and you are basically going to get exact solution in this case as well, because with only a concentrated force, the highest you can get is a cubic deformation, inexact solution. And since finite element is using cubic shape functions, so I need you to appreciate the fact that every time, so once you are done with the solution, once you do check that or compare that with the exact solution, okay, then I need you to appreciate the fact that whenever it is possible to map the solution in a given function space, let's say up to cubic functions, the finite element solution does give you an exact solution. Okay, that goes to show the consistency of the method that we are using. Okay, any confusion regarding what we have done today, or any confusion regarding the assignments?
No, sir.
Okay, so we'll meet on Saturday evening at 7 o'clock.
Yes, sir.
ওকে স্যার, আগে রেকর্ডিং গুলো পাঠানো হয়নি।
হ্যাঁ, আমি পাঠিয়ে দিয়েছি আজকে।